Welcome back to the Neuro Symbolic Channel. Today, we're going to review some original research that deals with what we call diversity measures as a way to quantify uncertainty in the output of large language models. So this paper, we have a preprint version that's currently available on arXiv, and we also have software available through GitHub. So here's the key idea. If a large language model has a variety of answers to a given query, then it's probably wrong. And let's think about this intuitively. So here's some examples with ChatGPT. So I wrote this prompt and it says, if I have 5 apples and you have 10, what is the circumference of a circle in apples whose diameter is specified by the apples that me and you have together? Okay, so that you can think of a circle and you have, 15 apples is the diameter of the circle. So can we compute the circumference of it, which will be 15 times pi? Now, if you look at the answers, ChatGPT at first says 45. Then it says 141.37. And then on the last two there, it says 47.12, which is more correct answer. Now, for this prompt, we have 4 different answers, and out of 4 answers, and out of those 4 answers, there's 3 different unique answers among the 4. So if you have something like this going on with your LLM prompt, it looks like, hey, something fishy is going on. It's not sure what it's doing. And if we look at maybe the second example, we fixed up the prompt a little more and, we allowed it to show its work, which I know often helps with things like, being more consistent in the answer. And here we see, in the ones I show, it says 15 pi apples both times. And actually, if you see all the prompts I put in this time, it was giving the same answer each and every time. So this prompt here is obviously a better formulation for this problem that I care about than the first one. And I don't even have to know the right answer, is what's interesting about this, right? I just have to know that there was less diversity in the solutions it gave me on the second time. And already that's telling me, hey, that, this might be more correct. And so if you think of, a lot of this really nice recent work that's been going on prompting and large language models, one thing that a lot of folks have been using is this idea of self-consistency that essentially is using the output probabilities of the model to calculate the probability of a given response to a prompt based on multiple queries with the same prompt. So you see in that summation, I equals 1 through m, and each of those i's is associated with a query for the same prompt. You have an indicator function. If ai, the response for prompt I, equals a, and then you have the probability of the output given p and q. Okay. And they found in this paper that this probability seems to closely correlate with the majority vote, which probably isn't too surprising, especially when you consider various parameters with the LLM dealing with temperature and stuff like that, where most of the probabilities that solutions are probably going to be very similar. And so our idea here is that, okay, let's say that a given prompt response, AI, is composed of some elements. And you could think of a math problem, asking it to, let's say it's solving for 3 different variables, A, B, and C. What A equals, B equals, and C equals are 3 different elements, right? And so we could have the probability of A being 5 based on a set of solutions to a given prompt. And that's what we're showing here, where E is an element. Now note that this is really well suited for cases where you have some kind of symbolic output, like result of a logic problem or a math problem. In the paper, we also do a bit of exploration into looking at stuff that is less constrained based on doing some stuff in the embedding space. But we're going to focus on the symbolic output. Those were actually the stronger results of the paper. So once you have that probability, then now you can compute an entropy measure or some other what we call diversity measure. In the paper, we have 3 of them, but the 2 main ones, entropy and Gini, which are common in many other things, seem to work the best for symbolic output. And that's what we'll talk about in this quick review. And so here is the entropy measure. And so let's say here's the first result we got. So we looked at 3 different data sets, 3 different types of problems, and we looked at about 5 different temperature settings, and we found a very strong correlation with the diversity measures. Here we see entropy for 2 of the data sets and the probability of the large language model returning the incorrect result. And so we looked at this cumulative with minimum amounts of the diversity measures, maximum amounts, and it holds actually in both directions. So this was pretty interesting to see that worked so well. So then the next thing is, okay, let's say for a given problem, just like the one I showed you at the beginning, let's say I have a whole bunch of different prompts and I don't know which one works best. And it might even be that in some cases one works better than the other. So what we did is for problems that we explored in the paper, we created a set of 20 prompts. And the way we did this was we held off part of our data set and we created each of the 20 prompts with a subsample of that holdout set. So it was we essentially were doing few-shot learning where the samples used in the few-shot learning were different for each of the 20 prompts. And as you can see here in the histogram, for each of the 20 prompts, each has a different failure probability based on a test set of data. And what we could do is we could take the diversity measure and for a given problem, run the problem through all 20 prompts, hitting each multiple times, and calculate the diversity measure for each individual prompt, and return the result that is the best one. And so what we found is when we did this, when we used the Gini or entropy methods, we obtained a significant lower failure probability than any of the individual prompts, and also better failure probability than the average across the different prompts. And so we see that in the chart here. And of course, compared to worst case scenario, it beats that out really well. And I think this is really useful if you are starting to create an LLM-based solution. Maybe you had a bunch of data that you use for few-shot development of prompts, but maybe the application that you're going to deploy it to, you might have some unseen data or something like that. And maybe to cope with that and the amount of potential error as the system is deployed, this might be an interesting thing to add on. So that was the second result. So then what was interesting is we thought, well, hey, this is great, but how does it compare with chain of thought reasoning? So for those of you who don't know, chain of thought reasoning is where you tell the LLM, hey, tell us each individual step. And we saw, as an example in the at the beginning, when the LLM explained itself, it did better. With chain of thought reasoning, also, if you're giving it few shots, you can give it kind of the reasoning that goes with each of those samples that are in the prompt as well. So to kind of teach it how to do reason about a thing. And what we found was when we compared chain of thought to the diversity approach, um, they converged upon the same failure probability. And you could see that with the minimum entropy selection, the dashed line in the chart on the right as you look at it, how it converges with the gray dashed line, which is employing chain of thought reasoning. And what was interesting though is if we used them both together, we got much lower failure probability than either of them by themselves. So they were synergistic to each other, which was a really cool thing to see. The other thing is, with this, as well as, the second result, we see, hey, we got 20 different prompts. This is starting to get expensive in terms of the number of queries to the large language model. If you got 20 prompts, each of them you're going to get, have multiple queries. But it seems that doing this, you converge upon a low failure probability after only a few of the prompts, like 3 or 4 or something like this. You don't seem to need all 20. So then the next result, we took all these diversity measures and we used them as features in a machine learning model. We actually tested a couple different classifiers. Here we see results for a multi-layer perceptron. But what we found is when we looked at precision recall curves for predicting failure in the output of the large language model to the query, that this type of machine learning model fed with features from the diversity measures does a pretty good job of accurately predicting when the failures occur. So anyway, I hope you enjoyed this quick video on this very recent work that we've done. Again, it's available on GitHub for download. The preprint's available on arXiv, and you can also check out the lab website. Thank you very much.